Hi, everyone. My name is Errol McLean from Georgia State University, and I'm currently doing an undergraduate in applied mathematics.
And I'm Thomas Sigler from Georgia State University, and I'm currently doing an undergrad in computer science.
And I'm Areeb Ehsan from Georgia State University, currently pursuing my bachelor's in computer science.
And today, for part of the SCUDEM VIII competition, we decided to do problem C, dog cannot catch, and we are team 1074 for Georgia State University. Given our problem, we are shown a video of a golden retriever known as Fritz as his owner tosses food for him up into the air in which he's supposed to catch it with his mouth. And one of the main focuses given our problem was how precisely does his brain have to estimate the orientation of his head and eyes to predict the location of the item or the food in hand. How much time will he have to orientate his mouth to the correct position? Whether or not certain foods are more difficult to catch due to air friction, and if the height in which this is or the food or the object is thrown matters. And we have to see what are the most important aspects of the dog's perception and behavior in order to successfully catch the food. So, what our model aims to do in relation to these questions determines on three factors. We have to factor in objects of different masses that will in turn see if they have an effect on how air friction makes it more or less likely for Fritz to catch the food. We factor in different heights and which the objects are thrown for certain foods to see how that affects the time for Fritz to catch the item. And how can we use all of these variables at hand to answer what aspects factor in Fritz's success? In order to start for our model, there were a certain amount of assumptions that we needed to make. Firstly, we had to assume that once the object hits Fritz's mouth, he successfully catches that object. It doesn't go in or out. We see that these foods are thrown at a similar path and hit the same spot in which Fritz has to catch it. We see that we have a set reaction time to study whether or not the reaction time we give for Fritz for this object to hit the spot is within a frame for him to catch the spot. So in this case, Fritz has a set reaction time given his circumstances, and whether or not that innate reaction time that Fritz has, he's successfully able to catch that object giving its motion through the air. The shape of the object at hand is similar, so we're seeing only the mass and the height of the object in which is thrown that differs between experimentation, and we don't factor in the height nor the length of Fritz's mouth in consideration of catching the object. We kind of assume that there is a meeting point in which Fritz's mouth hits the object, and that would count as a successful catch. So, given all of that, we have all our variables in hand based on a system of projectile motion of an object in the air pertaining to 2D motion. So we first have a x of t and y of t, which represent our horizontal position at time t and vertical position at time t, and x naught, which represents our initial horizontal position of the object, our y sub naught initial vertical position, which represents our height, v sub 0 of x, our initial horizontal velocity, and v naught sub y, which is initial vertical velocity. We have our acceleration due to gravity, g, 9.8 meters per second squared. Drag coefficient, as these next few variables all account for air resistance, which is a major part of our problem. A, representing cross-sectional area of object perpendicular to the motion. Our magnitude of velocity, and v, mass of the object at hand, which alternates in order to see the different times in which the object is caught within the distance, air density in rho, and a set reaction time related for Fritz in order that factors in with our model. So in the stages of our modeling, there were three stages that we considered when doing it. We brainstormed the type of differential equation most suitable for this side problem, which involved the throwing time of the object, a reaction time, and calculating the time it takes for the object to reach a certain distance to catch it. And we concluded to using a standard differential equation based off of projectile motion that factors in air resistance and reaction time. And we see that if this model constructed can be used with different parameters or in different heights and different masses in order to answer the questions in our prompt. And that leads us to this model here, where we have two problems that represent our x of t and our y of t. And our x sub t is x naught plus dx over dt, the distance over time, based on the time in which is set for the projectile motion to hit its spot minus the reaction time, and our y of t, which also relates to similar to our x of t, but factoring in air resistant components such as rho, c sub d, a, and v squared. And our dx over dt is related to our initial horizontal velocity, and our dy over dt is related to our v sub 0 y minus 1/2 the acceleration constant of gravity times our time. And our time in this case would be greater than or equal to our reaction time at hand.
Okay, so looking at some test cases, we generally chose test cases that were middle of the road and then an extreme one on the lower bound and then an extreme one on the upper bound. And we can see here that if we just take some variables and initialize them to these values, that Fritz generally has a few seconds to do a bunch of calculations in his head about where the object is going to be. And then he has to orient his head and mouth and to make the catch, which is not a ton of time, but a golden retriever's reaction time is 100 milliseconds on average. So we wanted to account for, a quicker reaction time than that because that's the average for a golden retriever, and a longer reaction time for that, and then perfectly average reaction time. And we can see that under this standard model, which doesn't take into account air resistance, Fritz has the possibility, but it's very, very difficult for a golden retriever under these circumstances to make a catch. And then we're going to utilize the air resistance portion of the equation to alter the trajectory. And we can see here that we once again chose something that was more middle of the road, a more extreme, and then a more extreme lower bound and a more extreme upper bound. And we're using the previous equations and we're just tacking these on to build onto them. And it shows that air resistance of different foods, it has to have a shape that is not aerodynamic or a very large area to make a significant difference compared to the previous results. The previous results often are, 100 milliseconds or around there, unless you start to get a very large area or very not aerodynamic food. So overall, most foods, the air resistance would not matter all too terribly much, but it can definitely make a difference, especially on larger foods. Finally, we wanted to answer the question of, does height have a significant effect when it's thrown compared to where the dog's mouth is? And we chose some heights that were about average, about for an average person, about how far their hand might be from the dog overall. And we can see, compared to the previous results, that height can have a pretty significant by adding a few seconds to the possible reaction time, which means that the greater the height thrown, the more time that Fritz would have to ascertain where the food is going to be and position his head and eyes, which means that it would have a positive effect on his catch rate. Here are some graphs that we made for the model. that shows for each example, once again, air resistance and height just built onto our initial test cases, the effects that each one would have compared to the mouth, which would be initialized at 0. And then these would be the results on the y-axis with just the time, which over time we would get to on the x-axis.
Now for our conclusion. The precision in estimating the orientation of its head and mouth with the goal of intercepting the trajectory depends on Fritz's skills and experience. Our initial hypothesis was that over time, Fritz would learn from experiences and the positive reinforcement from his owner will result in more successful catches. However, the complexity arises due to different foods having varying aerodynamics, making it difficult for Fritz to generalize his catching skills across different foods. Limitations 1. Unable to account for any other forces other than those specified acting on the food. The unaccounted forces may introduce unpredictable elements that would impact Fritz's catching abilities. 2. Unable to account for the 3D movement of food and orientation of the head in 3D space. 3. Unable to account for the environmental factors such as wind speed and direction. 4. Limited observational data from the video footage. Now, some of the potential improvements that we could have made. In our analysis, we focused mainly on 2 dimensions. However, for a more comprehensive understanding, we can consider the problem in 3 dimensions, which can explore how Fritz adjusts his position, not only vertically but also laterally, to intercept the thrown foods. Taking into account whether Fritz can jump to catch the food will introduce factors such as jump height and timing, which could become essential considerations. Refining the air resistance equation involves a more detailed examination of the shape and properties of the thrown food items. Furthermore, considering Fritz's age and experience level in catching food can also play a significant role.
And these relate to our citations here. Thank you very much. And we would like to thank the SCUDEM for helping us take part in this competition. We very much appreciate it. And we hope that our eventual model and results can be graded in a fashionable manner. Thank you.